Okay. So today we have 3 teams, and the first group, last Tuesday, they went very well. They did a good job, and last Tuesday, they controlled the robot using 60 gestures. And the other two teams, actually one of our 2 teams was presenting some the visions, computer visions to control our robot. And the other team, the last team, was presenting the mobile robot control using sensors. So actually they use the light sensor and then for fighting situations. So they went very well. And then today we have 3 teams. So hopefully you're ready for your presentations, and I'm very excited. And so we have very small group today, and then we budget 2 hours. So I would say each team could have up to, let's say, 25 minutes. So I will let you know if you hit that 20 minutes, so we can be at the right times frames. And then the same I just gave you the post-it. So the plus and questions, you can put that plus if you see that good or potentials and questions for your questions or any suggestions. So and then after each presentation, I will collect the feedback, and then I will give them to the presenters. So exactly same. So. And then, by the way, the also after these presentations, and any time by this Friday, please return your robot and let's say whatever you have, you borrow. So if I'm in my office, you can directly return those robots, any tools to me. If I'm not in my office, then please leave your robot into the cabinet in this space. And then, but if you plan to leave the tools or any robot in this space, please write down your name, deposit it, and then just put it to the whatever you're returning, so I can see who are returning those the robots. And then the red part, please disassemble the technical part for, let's say, the next class. So please disassemble the red part, and then I think that I will bought red part, and then some and also Raspberry Pi, and then some students, the Arduino. Okay, right then, who go first? Okay, you go first. Okay. Oh, I think your file is about 160 megabytes.
Yeah, because of the video.
Of the video, okay. I think the iPad.
We use a laptop.
I know. Oh, you're gonna use it. Okay, good. So iPad we like you because no, I'm just kidding. So whenever you're ready. Okay, this is cool. Okay, good. Yes.
Yeah. Okay. So good morning, and we call our project Robot. So what we have done is a robot which can cook and do daily household stuff in the things that are in the kitchen. So we'll go into it. So to get started, as you all might know, like robots are not like a thing of the labs or like some high stuff anymore. So we are moving into the future, and they are becoming a very common stuff. So it's not quite surprising that like we can have robots as a normal thing, like a refrigerator or something in our home. As you know, like the iRobot is also a robot, just used for vacuum cleaning the house. So already like robots are taking over the daily household tasks, and we want to take that kind of automation to a next level. So that is why we wanted to like bring in a new robot which can cook and help us. So what really motivated is that cooking is a really skilled task, and it can take time for a new user to learn cooking. It can take time to master the art, and also like when you go to restaurants, like they have a demand for really good chef. So you know that like all restaurants don't serve good food, right? The taste differs from restaurant to restaurant. So there's a really good demand for a expert chef. Also being a grad student, like we have tough time cooking. So that's why we thought like, why don't we automate this? A robot, make robot to cooking stuff. So this is where it all started, and motivated us to like a lot of nice interesting stuff. And so what we use here is we use a concept called programming by demonstration. So what programming by demonstration is, instead of completely like writing tons and tons of code, telling the robot what to do, we show the robot, which is obviously better. Instead of writing code, which can be tedious, may not have the expected output. So what we do is show the robot what to do. The robot sees and it does it back. So that's the whole idea of what we are doing. So how it all started was maybe in the early 90s. It was all sort of playback. So they set like a set of motions like move this joint by so much degree, rotate this. So it was all predefined. It was fixed, and the robot does it, and it can do a certain task. This is pretty much like the car assembly lines. It's perfectly programmed. It keeps doing the same task over and over. But thing is, for a cooking task, it cannot be used. So as you know, like when you're cooking, like the pot may not be the same location all the time, and sometimes it might run away. So we have to hold it, depending on like various dynamics. Like there are a lot of things which you need to handle, right? So pre-programming is not an option. So playback was not never an option for us. So as time moved on, people moved like started to teach to make program a bit more generalized. So the other robot like learn some gestures and try to do learn some skill based on that. So this was the beginning of programming with demonstration, based on something like show a robot like tell the robot like okay pick this stuff and something, and the robot already knows how to pick stuff. It tries to replicate the gesture done by the human user. So this is how the things are moving. And quite in the early 2000s, in the mid 2000s, there's something called kinesthetic teaching turned up. So what they do is like hold a robot arm and try to move it around. So you can hold it, and as you know, like we use like encoders a couple of things, right? So based on such encoders, the robot can keep a track of how each joint is moving, and it knows okay. So for this task, we need to do this, which is like bit more better and like robust as compared to like playback, like hard coding like joints, which can like do a task much better, but still not so generalized that we can learn a lot. So that is where like these machine learning based techniques like really like are making things a lot better. So we do a task, it observes how our hands move, how each part of the body moves, and it can generalize it by developing models. So and learn some parameters. So based on which it can keep doing something. So this is like how things are moving, and machine learning based techniques are like really useful and really good. So even our project is much based on that. So what were our objectives? So as I told you, like some motivation, our main objective was to build a chef robot. So make a robot which can cook and do some basic kitchen stuff like cleaning the kitchen, chopping vegetables, like so build a robot which can do these basic tasks. And how we wanted to build it was use programming with demonstration to train it. So the robot should be able to track all the objects in the kitchen, and also the instructor who's teaching the robot tracks both the person and the object at the same time, and then find out how the user interacts with the object. So it's like relatively like how what the user is doing with the object, like picking it from here, placing it somewhere. So it's basically like we localize where each object is and how the hands of the user is moving, and try to find the how the trajectories and learn how to do some basic stuff. So to make things simple, we wanted to like build an interface which will be easy to teach, also like and one more interface which will be easy to control the robot later. So as an end of for usage, we are using a robot called Super Baxter, which is like a bimanual Sawyer thing. Sawyer is like a arm from a company called Rethink Robotics. So Super Baxter is nothing but two Sawyer arms together. So I'll show you pictures of later. And so this was our objective. So going much more into programming with demonstration. So what it is. So if you go into a flight, and if someone gives you a big manual of the safety system in a flight, we may not be like quite motivated to read and really observe and learn stuff, right? It's not quite intuitive, like so encouraging to do stuff, and not so easy for us to understand. So different persons might have different perspectives. Each one might take the safety rules in a different way. So it is quite ambiguous. So that's why they have a person to demonstrate in each and every flight. It's quite simple. They show by actions, which are really easy for us to learn. So that's exactly like programming by learning by demonstration, sort of. So they show some actions, and we know, okay, how to just put the oxygen mask, know where the windows are, and so on. So that's the basic idea. Track what the user does and learn based on that. So the human interaction with an object are just like observed, and they're like made into a program, written by the computer as a mathematical model, which can be used to like do various tasks. So for each task, we demonstrate. Maybe for pick and place, we demonstrate it once. It observes and learns. So for every task, what we intend the robot to do, we demonstrate it to it, and it keeps learning and so on. The main challenge here is certain tasks can be quite difficult to observe. For instance, arm movements are like quite easy to like observe, like how I move this joint. But at finger level, might be challenging. So as the task is quite complicated, building a model for that is also gets complicated, like developing hardware to observe it. So with that, how that task is complex, using this idea also gets complicated. So the basic methodology what we use is we have a demonstrator, and he demonstrates a task, and we monitor it using a monitoring system, and we develop a robot task planning system. So from the demonstration, from the interface, it observes and it makes a task plan. It plans a task on how to do from a robot perspective, and then based on the request from the user at later point of time, it knows what to call, and it does the task execution. So it's like learn and then use it for later. So this is a Super Baxter robot which I told, which we're using. So this one, so nothing but like each arm is called Sawyer. So just like from the market. So we just try to use both of them together, and we call it Super Baxter. So this is our end effector. So this is a robot which does all the tasks. And our main interface was Microsoft Kinect. So it's a 3D we need to observe things in 3D. In the 3D space, we wanted to observe where each thing is, and also like how the user moves. So both for like tracking each object, for learning, both we use Kinect. So also like good thing about Kinect is like they have like SDK which provides us like pre-written code for like human tracking. So all the tasks related to like tracking a human, how the human moves his arms are already like given by them. So we just only have to use their interface, like then like make some inference based on the input given by their SDK. So that made like things a lot easy for us. And one more thing, like the third part was also an interface, two interface, one to learn, and other later to control it.
Yeah, so let me give an overview of how we actually do the inference. So basically, as Sham showed, this is our entire architecture, how we actually do it. So the thing is, robot is equipped with Kinect, which has both audio and visual. So right now we are using only the visual part of it. So we observe the entire task done from the human. So then what we pick up is basically all this human and object interactions. So we look at like how a human interacts with any object. So as we are tracking a lot of objects, it's not a good thing to just see every object and say, okay, like he touched this, he touched this. So we have like region of interest, which looks at human hands and it tracks, okay, if a particular object is within some area or volume of human hand, it tries to look for those objects and see what the human is trying to do with it. So then what we infer is when he interacts with it, then what he does with it. Like things like he approached it, then he grasped it. So then he's moving it to somewhere. So things like those is what we actually infer. And then we also look at object to object interactions. So basically the whole idea of any task, if you see, is to do some relative motion between objects. It may be some application of force, like you use a tool to apply a force. Here, the tool is interacting with another object. Like if you're using a screwdriver, tool is interacting with the screw. So it's like object to object interactions and human object interactions. So these are what we basically look for. And through the developed models, we infer these human intent, or what we call as human intent, which are based on these interactions. So that is the first part of it, which is written there as human task inference. So after the task inference is done, or we have an overview of what the task was, like to pick something, to scoop something, or like scoop it something and unscoop it in a particular place with some force, things like those. So then how the robot needs to plan how it can actually execute it. So since human architecture or configuration is completely different from how a robot architecture is, or like the arm is, you can see like super backstory is so weird, but human is like it's very intuitive. So to map these small skills from human to robot is like a difficult thing. So the robot needs to understand how it can execute each skill. So that's why what we do is like a robot task planning, where it can also infer things which were not captured. Like basically, if I touch an object, like Sham was saying, it cannot actually see if I am doing something with my fingers and things like those. So things like grasp and all can be based on how these skills progress. Like if I touch an object and it starts moving with me, I can tell, okay, now I've grasped it because I went and reached for it, and now the object is moving with my hand, which means I should have grasped it. Things like those. So that is what robot task planning does. It tells the robot this additional missing components which it can incorporate. And then the last part is the task execution, where from this inferred thing, a program is generated. So you just show the robot, and now you have a program to run the robot. There is no need for any programming anymore. So that's the entire architecture of how we actually do the inference. So as I told, it's mainly based on this object agent and object-object inferences. But what do we actually look at when we say, okay, we just look at the interactions? So what we actually see or look for is a set of observable priori skills. We call it priori because it's like we have developed models for it, and the robot already knows like these skills are like the basic primitives which any human performs or any robot can perform. So that is what we look at. So in this example, when we see like the Kinect, which is tracking the human skeleton, and we see the agent reaching for a particular object. So you see that like the small white boxes is like highlighting the objects. So we actually detect, okay, like now he is reaching for it. So he's about to grasp it. So it's like an approach kind of thing. So these are the different kinds of skills we encapsulate. Things like approach. Guarded moves are basically like you keep moving your hand until you contact some particular object. Then there is things like transport, which I told is the object is moving with you. And visual servoing is basically if an object is dynamic and not like static, for example. Then we can also see like our hand is moving with the object and trying to reach for it. So visual surveying skills are like slightly more complicated than normal skills because we use a combination of vision plus grasping. So things like we need to infer those. So those are also encoded into the robot. So these are different kinds of skills like scoop and all are like additional skills which are basically tool use skills. So these are the ones which we have right now. And what we do is basically through this priori skill database and object identification, we look for how these objects were interacted. Basically things like hand approached object, hand grabbed object, hand is moving object, now hand is placing object on something else. Okay, so things like those. So basically, for example, in a very simple task like making a cake or like you're topping a cake. So it will be like hand approach strawberry and it is supposed to pick it and it is supposed to place it on top of a cake, things like those. So that's what we actually mean by how we observe skills and this relative object thing. So what is shown here is after you do the execution and it does the inference, it generates the program. So this is essentially how a program looks. This is the flow chart of the program, of course, and for a very simple task is shown. So basically it uses, when it is running the program, it uses both the demonstration database or object database, which has basically like markers for the object saying an object A looks like this or a strawberry looks like this. So the object database contains properties of object or how they look, things like those. And basically the flowchart shows that, okay, if it's a pick and place object, so you actually try to find it. And if you find objects which are not there, just ignore them. And if the object is in the database and is also incorporated into the task you're supposed to do, try to move towards the object, try to pick it up. So we are like visual surveying, but what we do is like some predictor model to actually grab objects which are moving also. So we don't always consider static objects. We know objects can move around. So we do a predictor model, which is what's shown as visual surveying here. So then we move to the destination, like whatever the object destination is, pick it up. And then the program continues. So then the next reference position gets updated to the another object, which is the reference. And this also includes like gripper state and things like those. So that's essentially how a actually track cheese. That's what we found. So we put a bunch of AR markers, which makes our life easier, and we can track things around. So we can tell where it is and things like those. So for larger objects, what we actually do is we track it when it is moving with the hand. So here we also added things like inferences like, okay, if I reach for it and I do some contact with it, and then I'm moving it and my hand state is slightly changed, I mean, okay, I've reached for it and I have grabbed it. Things like those is what we say there. So that's why we use a bunch of AR markers instead of tracking cheese or corn or things like those. So then we set up some 3D tracking for them using Kinect. So our entire demonstration is shown here. So this is the entire setup of the robot. So we use both the arms. Show a very simple demonstration of how we can make a taco. So we put a couple of things like beans and some salsa and add some onions, so jalapenos and corn, and we just make it. So the robot tracks both the arm movements, the scoop, the box. So we also do things like region of interest. So we look only at the table and the human arm motion separately. So there is like a smaller cluttered space to actually do it. So this is the tracking part of it, where you can see like there is rice box identified, saying okay, the rice is there. Then there is the scoop, which is identified to this bottom left. You see like 2 dots on the scoop. That is actually to check what orientation the scoop is moving at and so on the top left, you see like all the AR markers which are being tracked and what I'm interacting with. So we didn't put the Kinect skeleton video because anyone would have seen that. It was in one of the images which you saw it similar. So what we essentially learn from this is like a sequence of things which needs to be done, where like priorities for objects and the things like how we need to interact with each object. So if it's like black beans you choose, so then it's supposed to scoop it and not pick it up. So things like those we try to do. So this is actually Super Baxter doing the same thing with its configuration. So it is trying to make the taco there. So we selected a bunch of this one. We'll show a close-up of how it is selected. This is the tracking part of it.
Yeah,
like, so the thing is, we know some of these markers will lose tracking sometimes. So what we do is essentially, whenever it loses a marker, we have a estimator to give what the previous position was and give the old position. So this is the interface how we choose. So for example, we just chose a bowl and we told it to make car. Just play that. So, yeah. So this is the GUI which we made for actually interacting with it once it has learned the tasks. So people can select. Of course, you see things like burrito, which we were not able to finish, and because rolling burrito is like complex manipulation, which is if we do that, we can write a bunch of micro papers. So that's what we realized. But then we do tacos and bowls and salads. So we can actually select all the taco, bowl, salad things. And all these other things we can actually interact with. So the GUI is like very simple and intuitive. So people can just click on a bunch of things and say prepare. And based on how each object needs to be interacted with and what it learned, it will try to do that. So for example, because we selected black beans, it tries to scoop black beans into the bowl. So basically it made bowl. So it can make bowls, tacos and salads and things like those, which are simple things like even sandwich and burgers right now. But it's not always, it doesn't always work. So, and the reason is because it learned the positions based on human offsets.
Oh.
So things like these happen where it split the entire rice. So yeah.
So are the positions also fixed? Like this will move in
Tracker? No, it keeps tracking it. So, but whenever if it misses tracking, what it does is it will update whatever the last position is. So if one of the trackers falls off, or for sometimes because Kinect is the illumination changes on these AR trackers, they miss the tracker. So what we do is we just say, okay, if you are missing the tracker, just use what the last position was. Things like this. So you can just move around the objects wherever you want. It doesn't matter. But as long as it's detecting those objects, it will reach for them. It doesn't need to be like at a specific position. The position actually doesn't. So if you see this is how it actually tracks. So on the top right, you see like this AR markers, which are all tracked. And you see below that, there is like all the. So if you see on the bottom right, there is even taco and like the bean box and rice box and things like those. So it tries to detect all the objects where they are in the 3D frame. And based on that, it tries to move it. Yeah, so essentially what we did was have fun. And we got to make a bunch of free food made for us by the robot. Not that everything was good, but it was somewhat fine. So the idea was like to make a chef robot. So right now, a robot can do simple tasks like make a sandwich, anything which involves like scooping motions and pick and place and things like those. It cannot do complex manipulation like rolling a burrito and things like those, because just grabbing a tortilla is difficult for it, as tortilla is like a flexible, weird object. So yeah, basically it can do all these simple cooking tasks, so we can put it in probably Chipotle then and try to make some money. So these are, and we have developed this routine for actually learning from human how each subtask can be done, like how beans can be scooped into something, and how objects can be picked and placed, and what is the sequence of those objects which needs to go into making a particular dish and things like those. So our learning-based routine will actually help you do that. And we also developed the GUI for interaction with the robot and things like those. And the essential thing is we can assist humans in kitchen now, a little at least. So yeah, so there is this company called Molly Robotic Kitchen, which they are coming up. They started last year or something. So they have a video on their website, which is fake, obviously, but they have like a CG video kind of thing, which they show a robot handling chopsticks and yeah, things like those. But basically, they are trying to do the same thing. They're trying to put two arms and actually make a robot which is for like a kitchen. That their startup is entirely based on this. So there are some people who are trying it actually. So that's a good thing. And some future work which we want to do is try to actually understand how complex manipulations need to be done. Things like stir frying, where like you do this motion. A robot does this now; it spills everywhere. So things like those. Then bimanual collaboration is something it doesn't do right now. Like how it can have both hands together apply force on an object. Because if it's a rigid object, we know if both arms apply force, it can break it. So we need to do how it can actually handle force-based bimanual tasks. And also, right now, since we are using AR trackers and things like those, we want to develop 3D object recognition, where it can actually detect smaller objects like like cheese and all these things, if it can do it. And we also need to, we are planning to add a speech interface instead of just saying this. So you can just talk to it and order things. And the other thing is how we can actually teach physics to the robot. So that whatever cartoon you see there is like how the robot thinks it right now. So if we can actually teach how objects will behave in the world. So things like if you go to a particular place and drop an object, it's going to go down. So the robot can learn things like those. So teach physics kind of thing to the robot. That's what part of plan for future work. So this is the individual contributions. So we had a demonstrator and worked on inference routines, and we had some Sham working on camera calibrations and air tracking, things like this. So yeah, thanks for being patient and listening to us. And that's essentially what we are doing, removing all programmers, which is essentially putting myself out of job. But it's fun, so yeah.
With the current gestures that you're able to teach with the robot, do you think you would be able to teach it to squirt like a bottle of sauce onto the taco?
Yes.
Yes?
You
Okay,
can. But
cool.
but the thing is, when you grab a bottle of sauce,
You have to
you need to squeeze it.
orient,
Yeah. You need to orient. So things like orientation, it can actually learn from the current gestures.
Cool.
But things like squeeze, it can't learn because we can't really detect squeezing from Kinect.
Yeah, that was
So that is some part of things like object physics which we can add to it. That's what we want to work on.
Sure.
Where you can add physics to objects, saying okay, such kind of bottles you can actually squeeze to get some fluids or things like that.
Sure. Yeah, that's
Yeah.
cool.
How accurate is the Kinect in a 3D space? So if you move
Kinect-
from here to here,
Oh, Kinect is not really
Yeah.
very accurate. So the errors are anywhere between. It also depends on how good the identification goes on. But basically, just the Kinect, if you see the point space, the error is around anywhere from 2 to 3 centimeter at least, minimum. So. So the idea is eventually we want to add a camera on hand, which is much closer to the object, so resolution is better and we have closer tracking to it. Yeah.
Question?
If you if you're picking up the cheese and you're
Yeah.
trying to grab the cheese, and then
Yes.
as you move, cheese falls. Would it
Yeah,
be
yeah.
easier to put a small scoop underneath it to let go and then carry it across? Would that help or be?
Probably it would help. Maybe for some things that makes sense. So even we do that. When we think we have a hand under it so we don't spill. That's actually a good idea. But yeah, we can actually do that.
Okay.
So if it is, since it's just a trajectory move with the hand, we can infer those things. But if it is something together, the hand is also holding, that is something which we can't do, right?
Yeah. So, how many times you need to teach? Means you need to
Yeah.
show the
So
gestures
our
in front
idea
of the
is
robot?
the learning is just one shot.
One shot.
Yeah. So you teach it
But
through
that
one
will
shot
only
learning.
repeat whatever you did.
Yes.
But it won't be doing
The
I
same
mean-
thing. Yeah. It doesn't do the same thing. That's the whole idea. So it actually tries to infer from one demonstration everything it can infer, all the subtasks. So the subtask can be replicated later.
Okay, so the subtasks that you have divided, you have put markers on
Yes, it's
those
annotated,
subtasks.
yeah.
So
So
whatever
there is
subtasks,
so-
there can be many more subtasks that
yeah.
you can define and
Yeah.
these kind of things.
So we just need, we actually just need to annotate it saying, okay, this time frame to this time frame, I did this kind of thing. So then it can extract it. So if we need a sequential learning, we can just say, okay, this time to this time frame is a sequence of things you need to do, understand, things like those.
Okay.
But there are some times where there is some ambiguity, so it won't exactly know what you did, or the inference won't be correct. So that's why we are trying to so there's a part of thing which we future work where we are going towards this coaching. So we try to teach the robot do a error correction through interacting with it through speech and audio kind of thing. So it's how humans coach. Basically say, okay, you did that wrong, try to move your hand, little things like those. So there is this work on error correction which we are starting. Yeah.
Okay.
Does it do commands one by one? How it moves, drops? Can it do both at the same time? So
Yeah,
Okay.
it can grasp
I just
and
didn't-
do things. Yeah,
I just
here it
didn't do
does.
it
Yeah,
in your
yeah.
definition. I just
Yeah.
wasn't sure.
It can grasp and do things at yeah.
Any other? Very interesting. A lot of potential. couple of questions, and I have a lot of questions, but I'm thinking the time frame that we have. So now you use a Kinect.
Yeah.
So I think that the challenge is addressing
Yes.
about object
Kinect.
detection
Yeah.
on Kinect. So what if you could use a Vicon?
Vicon is actually much more precise,
but
then it requires a setup. Yeah. And the setup is also like you need 6 cameras or 4 cameras at least to be around.
So do you use only one Kinect?
We use only one Kinect.
Only one
right
Kinect.
now. Yeah.
Okay, I think also another the question is that let's say we saw that the video and it is interesting and then very impressive. Now let's say it's a supervisor when he or she decorating some the ingredient, we see that it seems it could go there some dishes and then but it seems it doesn't know whether it grabs or not.
Grasp
How-
confirmation. Yeah.
yes.
So
So it seems if there are no feedback loop.
on the left hand there is a feedback loop. On the right hand, so for the 2-finger gripper there is no feedback loop actually. But on the Barrett hand we do have a force-based grabs. So where we say like try to grab a particular object with a force, and if it fails or like if the force is not reached, we say okay it
But
failed.
human,
Yeah.
let's say, we use not only force
Yeah.
to detect whether
It's
I grabs or
yeah.
not, right?
Yeah.
So we use that even the vision
Vision,
and
yeah.
even smells, I don't know, so
Yeah.
all the sense, right?
Smell and-
Sensories. So I think that will be you might
Yes,
think
yeah,
about
yeah.
let's say future
I think,
directions.
yeah. So because right now the right hand will have no confirmation whether it grasps or not. Yeah.
Another is, let's say, I like that idea, the by demonstration, the human demonstration. The fingers, I think the arm, so we have about 60 degrees of freedom, our
Yeah.
arm. For finger, we have more than dozens.
Yeah.
The freedom, right, degree of freedom. But the hand is that you show that
Yeah, one of it is just 3
So,
fingers, the
yeah,
other
3
one is
fingers.
just 2 fingers. Yeah.
2 finger and 3
Yeah.
fingers.
Yeah.
So how you
Map the
yes.
yeah. So that's the reason why we can't do like complex manipulations with fingers. So we can do only things like grasping or like we can't do something like rolling. Those things we can't do it. Yeah. So we are trying to do something like have 2 hands work on the same task if we can to do that. But right now we don't have that. Yeah.
Okay. So now I think that obviously it should be very doable. I think it's good. It's very doable if you that supervisor, if he or she does that very repetitive task, something just moving or wrapping
Yeah.
or just chopping. I think that is very doable, and also it can be achieved by the human demonstration. Now, what is your envisioning? So, do you envision that your supervisor can do, let's say, cooking for everything, or just you could start from the beginning task to the advanced task?
Complete cooking might be like a really
It's still a
challenging one.
challenge,
Like
yeah.
all the tasks in cooking is like a long way to go. It involves a lot of degrees of freedom for the arm. Maybe like halfway can be like from the basic part like chopping, getting all the stuff ready. Maybe like stirring the thing. Like maybe like if your food takes long time to cook, you can just it can do it. It can put all the stuff. You can keep stirring the thing. But like few things might be complicated. Like the tossing the pan. Such things might be like a far way to go.
Yeah.
I like it.
It's boring. The entire process.
Mhm. I'm not really. I don't wanna really ruin your idea. But one thing, another direction, another angle you could see is, let's say, assistive robot. Let's say there's a main chef.
Yeah.
And then, so I don't know, if you go to fancy restaurant,
Yeah.
there could be groups of chef, right?
Yeah.
One is main
There is
chef,
hierarchy,
and then
yeah.
hierarchy,
Yeah.
right?
Yeah.
So then it could be, something also collaborative, right?
Yeah.
Not only by demonstration, also developer interaction, and also some gesture interaction. So also there are another the angle you could approach. So a lot of potential. Okay, so it's good. It's really very exciting, and then new researches and new projects. So I think that is that your, let's say, research project that you are.
This is actually the learning part of it is part of my research project as well. So.
Okay. All right. Any other questions? Right. Good. Yeah. Thank you so much. Can I have your feedback? I like your orientation. Okay, good. Thank you so much. And the next team, who? Okay, and then you are the last.
Good feedback.
Okay.
Oh, that's fine. It's some font that we have. It yells at us every time, but it still works. So
Okay. Yeah.
some font package to transfer over from the drive. Since Daniel's in the bathroom, we're just gonna open up our videos because we had problems with embedding the. The embedding didn't transfer over from Google Drive. A little frustrating.
No, it just goes straight to the custom
Well, I know, but like it's not embedded in.
Okay.
Do you want us to start with that?
Yeah. That's
All right, hey guys, we are here obviously to present our CNIT 581 project. We ended up doing kind of a VR suite mixed with a camera that's adhered to the iRobot to enable us to see through the robot's eyes. I'm Andrew Tidwell.
I'm Michaela Farrington.
So as you all know, our task was really to apply the software development principles that we've learned in this class and in other classes, just in CNIT in general, and create a robotic solution, a custom robotic solution. Like I said, our objective was really to allow the user to kind of have a robot point of view to see through the robot's eyes by utilizing Raspberry Pi camera and a VR headset. Our motivation primarily lies in the fact that we're incredibly interested in VR development. Both Michaela and I have done some independent work with it. We've never actually been able to kind of find the time to make an application. So we figured this was like the perfect setting to actually, kind of explore our interest in VR and make something fruitful. Like I said, we really wanted to integrate robotics and VR because we're both really passionate about those two subjects, and we thought it would be really cool to kind of have a immersive feel to a robot to actually be able to see what the robot sees. And I actually own a Samsung Gear VR. I got one recently for Christmas. So I figured it'd be kind of fun to play around with it and actually develop something for it that I made myself as opposed to just, downloading something from like the App Store. So, like I said, our background is really just that we wanted to make a VR-controlled robot. Initially, we had really hoped that we would be able to get the functionality of the Gear VR controller working to actually physically control the robot. Unfortunately, that proved to be incredibly difficult. We're going to explain that a little bit later in our analysis. But ultimately, we decided that we were just going to go with the keyboard, just using like arrow keys via the Raspberry Pi. It's pretty similar to what we've experienced in lab in the programming assignment. And also to actually view, like I said, we're going to be using the Samsung Gear VR headset, and we're going to be viewing from the robot's perspective. So here I just drew up a little bit, like a quick little deployment diagram. I wanted to kind of show our system as a whole. There's really two subsystems to it, the VR subsystem and then the Raspberry Pi subsystem. That we developed. The application utilizes Unity 5.3. You have to use Unity 5 or higher to develop VR. That is the only Unity version that has the Oculus API and Oculus support built in. Otherwise, it's a real hassle to try to get the Oculus integration. So we just went with the version 5. And we also utilize C# scripting. I'm going to explain later more in depth about the APIs we used, but for our VR application, we used a YouTube data API version 3. The version 3 had a lot of capability that was very pertinent to our project, and it actually made things a lot easier, honestly. We got really lucky finding that. Obviously, we used the iRobot. I mean, that's kind of a given. But to control the iRobot, we developed kind of a rudimentary Python application. I mean, as I said, you guys are very familiar with it. I mean, it's basically the same thing we did for programming assignment 3, but instead we're just using the arrow keys as opposed to a GUI. So it's just a little bit more streamlined because, again, we're going for that immersive feel. That's really the goal of this project, is to get a user to be fully immersed in the robot's world. So we really wanted to try to find a control that would allow us to, you know, basically be as immersed as we possibly could within the time frame and the constraints of our project. We utilized the Raspberry Pi 2 and the motion library, which I'm going to go into a little bit of detail later on. A USB camera, I believe it's ELP USB camera, and then a web page. It's a very simple web page. I mean, we didn't even really, the motion library actually handled a lot of the creation of the web page. We didn't have to write like any HTML or anything. It's just ported directly from the camera streamed to the website. So it was very easy implementation as far as the motion library was concerned.
And so then one of the first approaches we had to take was, how do we have video? So what we did, like Andrea said, was stream the camera feed to a local website. And we used the motion library for that. And like she also said, it just handled all of that for us. So we really just basically found a tutorial and followed that. And then what we first saw was that there was like a 5-second delay between one picture to another capture. And we were like, that's not good. So we decided, once we messed around with the settings a little bit, we changed it. So if you're on an actual, like connected the Raspberry Pi to a monitor, you can see it's almost like completely live. There's only like milliseconds delay. So it's not really noticeable compared to, we also, you'll see later, we have a demo video of starting the motion library, and that has a huge delay because that was reloaded into the Raspberry Pi. So you'll see that later. But we use that just to get the camera feed and put it on just a local website. Then we encoded that into an MP4 format so that we could have like a data type like format to actually use. And then we took that video and put it in the Unity VR environment using socket programming. This was like our initial idea of how we wanted to do everything. And then later on, we'll explain what really actually happened.
So I'm going to go ahead and go into our C# implementation, which is really the bulk of our project, because our goal ultimately was to create this system utilizing purely C#. We found that that would be the best venue to, you know, get all of our communication. It's directly implemented in Unity. C# scripting is just a feature of Unity, so it was very straightforward to utilize C#. And personally, it's my favorite language. So I was like, why not use it? I haven't had a lot of chance to use it anyway. So we were originally planning on utilizing C# for the entire system. Ultimately, we did not go that route. We'll obviously explain that in our results. But initially, our plan was to control the iRobot via the Gear VR controller. This kind of had its ups and downs. The Gear VR controller is quite complex, honestly. It's very confusing, and we had quite a bit of problems with my version of my Android OS because I recently just upgraded to Android 8.0 Oreo. And I noticed that after the upgrade, my controller started having a lot of compatibility and just general connection issues. And Android Oreo literally just came out. So, I mean, my phone was one of the first phones for it to be rolled out on. So I'm not surprised that there's a lot of compatibility issues that they're still trying to work through with Oculus, because again, this is developed by Oculus. They do have a pretty tight-knit relationship with Google, but still it is two companies trying to work together. So you know how that goes. But the Gear VR controller does utilize the Oculus API, and specifically there's an OVR input class within the API that enables you to basically get the controller type, because Oculus does develop two different types of headsets. They develop the Oculus Rift and then the Samsung Gear VR. So you actually have to handle what controller type it is before you can even really get into any of the click events or the gestures or the trigger or anything like that. So first you have to handle the controller type, and then you actually can go into your click events. In our click events, our goal was to do the iRobot commands. That was utilizing serial port class, which is system.io.ports. It's a very basic library for C#, if you guys are familiar. Also, as you guys know, for the program assignment we just basically created a byte array, sent that command off to the robot. That's basically what we're doing here in C#, except we found it much more viable to create an enumerable byte object, just because it's much easier to loop through each byte individually, just with the IEnumerable interface. It's a really great interface built into C#. I use it all the time. So we basically just enumerated a byte array, essentially, and then sent that command to the iRobot. Like I said, it's very similar to the 146 drive command. That was kind of the equivalent of it. It's just in an enumerable object instead in C#. It's kind of nice. C# gives you that functionality over Python. So that was why we really chose C# initially. Also, then we would just write the command to the serial port directly, write the object to the serial port. It's pretty straightforward, as you guys know. So also, we were originally planning on using the accelerometer to track head movements. So the servo motor commands basically utilize it's the Dynamixel API. It's the manufacturer of the servo controllers. Essentially, all you're really doing is creating a data packet of the serial information. So, general port, baud rate, all the kind of general serial information, and also a couple of specific things about the motor controller itself. And then you're just sending that information off from the motor to the motor controller. Now I'm actually going to talk about what we really did, because our approaches were pretty sound in theory, but then implementation was a little bit different. So as I said, the Gear VR controller was very difficult to maneuver with, especially given my recent upgrade of the Android OS. So ultimately, just kind of given the time constraint and general limitations of the project, we decided to go with the keyboard control via Raspberry Pi. Like I said, this is just a basic Python application. I think it's Python 2.7, utilizing arrow keys, just basic. Like Michaela said earlier, we were able to actually stream the camera feed to a local site. So we used the Raspberry Pi motion library. That library proved to be very fruitful because it's basically just a couple simple commands. I mean, sudo start motion, sudo stop motion. It's very straightforward. The only caveat with that being that you do have to configure the configuration file. There are quite a bit of parameters that we changed, such as frame rate and different stuff like that. That's what she was saying, how initially when we first started testing out the motion library, our frame rate was horrible. I mean, there was probably a 5 second delay. And we were actually able to tweak that configuration enough that it really ended up being about milliseconds. I mean, there's not a really large delay. However, once we ported that feed to our Unity VR, there was obviously a bigger delay because now we're dealing with networking and communication. And as we all know in IT, that can be a real headache. So we utilized the YouTube data API v3 that I spoke of earlier. This API was incredibly fruitful. We were not originally, we didn't even know this existed when we came up with the project and we proposed the project. However, this actually had a good majority of the functionality that we needed for the video itself. So as far as the process of getting the video from the local site to the Unity VR, we really needed to find a way to handle the data because it wasn't being typed. There was no file format to that video. So we had to end up encoding the video stream to an MP4 format. This was actually done directly through the API. They have very straightforward libraries, documentation, very straightforward to encode videos, especially live streams. And that brings me into my next point about the YouTube API. It supports live streams. And that was a really big point for us because this is a live stream. You know, a lot of APIs, video APIs specifically, do not support live streaming, especially being ported from a local site. This one actually did. We were able to play back the stream in a VR environment. So we were able to kind of faux a 360-degree view, which is another plus. Again, YouTube API is great. It was another plus of the YouTube API because they actually enable us to have a 360-degree without utilizing a 360-degree camera. So that was pretty cool because obviously as far as limitations, Michaela's going to talk about this later, but as far as limitations are concerned, we were really limited as far as like the hardware, the camera itself in VR, because you really, to create a true VR experience, you need a 360-degree camera. So, however, YouTube actually will wrap your video 360 degrees without you doing anything. I mean, it is automatic. It's a really great service. The API was wonderful.
So then moving forward, the results of like exactly what we did. So this is how we went about like the motion library and actually streaming everything. So like Andrea, oh, we're on the tablet. Okay, so then it's just like easy sudo service motion restart, restarts the whole library, and then you just type sudo motion to start streaming all of your video. So that's what that is, and it says it starts the daemon mode that they have, and then this was remoted into we remoted into the Raspberry Pi from my Mac, so that's why you see this huge delay. But even as this, like, this is only 1 or 2 seconds or so, and this is just a remote desktop. But that's how we got that part to work, and then
This was tricky.
okay, that's what I thought. So then this is our demo. So as you can see from the beginning, this is just playing a 2D video in a VR space. So that's why you see the little city behind it, is because this is, you're just sitting in VR, but it wants you to have this 3D atmosphere still around you too. So that's why the video is like curved. So if you're sitting and looking at it, because if you were still looking at a 2D thing, it'd be like sitting in front of a blackboard. You wouldn't be able to see as far up in the top as you could see in the middle. So that's why it's like squished a little bit. So it's more like looking at a map in front of you, like a paper. And then the video on the left is a paused video of the one on the right. But as you can see, this is if you just took it and wrapped it completely a 2D video as a 360 video. So what you're looking at is just the 2D video wrapped around you. That's what this whole moving around is. It's literally the bottom of the video as if you took it, you just folded it in a circle and then looked around. This is what you would get. But as you can see with like the limitations that we have with hardware, with not having a 360 video, this still gives you the experience of being the robot. And then as you can see with that video, you can still see the IR sensor from the charger. the demo that we had of how we went about all of that working. And then some good things that happened with this project was we got to experience VR development, because one of our initial motivations for this project was VR and learning how to use it. So we got that accomplished. And then, like you saw, we met our project objective, which was experience VR from the robot's perspective. So we were able to do that. Even though it's a 2D video, it's still like you're looking at a map, and you can see everything. And then one of the last things that we really didn't really expect to happen almost was expanded on our project management skills. Because there were only 2 of us, we didn't think it'd be that bad. But the fact that we had to make blog posts either like every other week, we decided to make them weekly. But having a post that you'd have to make every week, you can decide, okay, what did I actually get done within this week? Rather than every 2 weeks, you're like, oh, I did so much. But having just a weekly blog post, you can see what'll happen if you kept up with your goals and see that you're also moving forward. So like the motion library that we found that like on our second try. One of the first things was the built-in camera. Yeah, but the built-in camera module is a different kind of library that you have to use compared to the USB camera module. So with that, like we can see, okay, that didn't work, so we should stop trying to keep going with that and then move forward and try to find a different solution. So that's just with basic project management and how to like keep moving forward with the project rather than getting stuck in one place. Then some bad things that happened, or not so great things, were the controller compatibility issues with the iRobot. So how, like Andrew already explained, really, we ran into the problem of C# not working with the controller because her updating the software, and then also like the iRobot and everything. We were looking at it and we thought about it how we used it in class with a programming assignment. It was completely tethered compared to like if we're going to control it with a controller that's wireless, but we don't have any kind of wireless connection to the iRobot. We just had that serial communication cord, which to make this wireless, we would need something else.
The controllers are purely Bluetooth, so there wasn't really a way to tether the two. That was a big problem we ran into.
Yeah, and then the servo motor configuration. One of the big issues, because we just had one of the basic sample read-write programs, was the configuration software that came out. Like one of the requirements is do you have Windows XP? So it hasn't really been updated since then, and we both have Windows 10 computers. So when we downloaded it, it just did not work whatsoever. It like opened the program, but it wouldn't like actually configure anything. So that's the problem we ran into with the motors. Whereas if it was compatible, you just set up the software you pick your COM port that the motors are on, and then you select all the parameters that you have, then just hit configure, and then that configures the motor for you. So then you can try all of the example programs. Whereas we didn't have that configuration, so we couldn't try the rest of the example problems.
So as Michaela mentioned earlier, we did have quite a bit of hardware limitations. One of the primary ones being tethered connections. As we've all experienced with the iRobot, it is tethered. I mean, there is a serial port, a serial USB cord. You only have so much space to work with, so to speak. So we really kind of ran into problems with that as far as the camera was concerned, because the Raspberry Pi only has so much cord, the robot only has so much cord. So it was just kind of trying to figure out the best way to demo our app within the confined space. And again, as she touched on, the controller actually needed to be tethered. And we really did try to find a workaround, like implementing wireless, but as my next bullet says, we were really incapable of wireless communication in this project, just given the limitations and constraints of the project naturally. Ultimately, this we'll probably touch on in our future works, would be to actually implement like some kind of Bluetooth functionality in the iRobot to be able to implement the controller ultimately. Another one, a really big one, honestly, considering this is a VR app, is low resolution camera. That kind of killed us, honestly, because as you can see, I kind of wanted to point back here, because even though it is, it is this one. Yeah. Even though it is in the 360-degree view, it is so pixelated that it's honestly hard to tell exactly where you're at. It's honestly really disorienting. I mean, we both tried it in the VR, and it was we were kind of dizzy afterwards. So having a high resolution is prime. I mean, you have to have a high resolution camera to be able to effectively create the immersive environment that we were really going for. Ultimately, you also need a 360-degree camera because it really, I mean, while YouTube does create some really, or does have some really great API and code, it just really doesn't work without some kind of 360-degree functionality. But ultimately, I mean, we still were able to complete the project, meet the project objective given the restrictions. So like I said, I mean, there really wasn't insufficient immersion experience. The user, as the user, I really didn't feel fully immersed in VR like you often do when you're playing a game or when you're, you know, maybe watching a Netflix video on VR where you can just look around and you're in the video. I didn't really have that feeling, honestly. It was more of just kind of like a movie, like a theater screen effect, which was still cool, but ultimately, like I said, it kind of hindered the whole immersion aspect of the project. And another big thing was camera stability issues. So I'm going to touch on this in the future works, but we really had a lot of issues with stabilizing the camera well enough that, you know, it didn't make you dizzy when you're in VR, because again, VR, it can be really disorienting at times if the camera isn't doing exactly what it needs to do. So a couple of our takes, you know, the camera would fall a little bit, just slightly enough that you'd then be diagonal and you're looking around diagonally. Like it was just very disorienting. So we did have quite a bit of issues stabilizing the camera itself. So conclusion, VR development is freaking awesome. We loved it. We had a blast doing it, honestly. I developed a very rudimentary app that you could use the Gear VR. This was before I upgraded. You could use the Gear VR controller to like click a cube and the cube would spin in the opposite direction. And I was so excited about that. I was like, this is the coolest thing ever. And it was, you know, super basic. So I just think VR development is really fun. I know Michaela feels the same way. Another thing we really wanted to mention, because both of us kind of came to this conclusion once we were doing all of our reflections on the project, was that we really believe that this would be most beneficial as a full semester project implementation, just because as far as our project went, we feel like if we would have had a little bit more time, we might have been able to kind of work out some kind of solution as far as the Bluetooth and the controller were concerned. And also trying to implement the motors, maybe, you know, trying to find some Windows 7 machine on campus or something. But honestly, we didn't really have a lot of time given we're both seniors and trying to complete other coursework. She's in senior capstone. So we were both pretty pressed for time this semester. So honestly, we both kind of came to the conclusion that we would prefer if the project would be like in like January or February. That was just something that we thought, I don't know, maybe for the future. But lastly, pretty important, communication is key in healthy relationships and also healthy programs. That is a tenet that all of you need to live by, because communication can be a serious barrier to entry when you're doing any kind of programming, as we all know. Networking, I mean, half the time it's most of your problem, you know? So communication really did hinder us in this project, but I think ultimately we really did pull through and were able to find viable solutions to meet our objective.
And then lastly, all of our future works that we have. So like Andrea's mentioned, we wanted a more like immersive experience. So to actually get that, we would have had to use a 360-degree camera, and then implement the accelerometer data with the head tracking. So like our initial goal was, if you turn left and right, that would turn the robot left or right. And then when you pan up and down, the motor would then turn the camera up and down. So then that gives you the full I'm moving and I am the robot kind of experience. And then, like Andrea said, using the Gear VR controller, and we wanted to do a 3D printed gimbal, which is basically a 3D printed stabilization stand for the camera, because that really gives you like the stabilization that you need so it's not falling everywhere, and then it's actually docked on the camera, so it really just doesn't move. And then one thing we thought would be really cool, so once you got all of that set up with the 360 and the controller, we would think autonomous mapping with like point and click, so you could be in a one space and point to a certain spot, because how the controller works, it has like a beam basically going out of it. So you could point to a spot, click, and then it would just automatically go to that space. So for that, obviously you need more sensors like ultrasonic sensors telling you distance. But then one of the things we thought would be really cool would be like a path mapping. So it could be on your computer and like have a 3D space like mapped out. You could click different places. So you could make a little path for them to travel and then just hit go, and you could like sit there and watch like yourself as the robot navigate through a path.
I was thinking too, like the simulation software that St. June presented on would be kind of cool for that, because you could literally like map a path and then see it physically. So something like that we thought would be really, really awesome.
And then our individual contributions that we each had was, I mainly did research with the camera and streaming, and then the servo motor implementation and the reasons why it didn't work, and then why we had to move to different things. And then the APIs was, I found the YouTube API and the initial like motion library that we used.
I researched primarily all VR stuff. So I did the Gear VR, and I also researched a lot of Unity VR development. I forgot to put this on there, but Oculus has most of the documentation for the VR, given that it is their API that you're primarily using, especially for the controller aspect. So I did a lot of research into the Unity and the Oculus VR development. Like I said, I made that demo app that was, it was very simple, but it was just basically a proof of concept of, okay, we can use the controller. But then of course, you know, like it goes, I upgraded and then the controller decided to stop working. So we unfortunately, like I said, weren't able to do that. But ultimately I did end up developing a lot of the final app. Michaela helped a lot with the YouTube portion of it, because there was documentation, but it was still a lot of trial and error for that part of it. So
Thank you. Any questions?
Question?
What do you think in case we move to a really high resolution like a HDVR camera? Will there be like a delay in the streaming? How's the API working? Is it like really fast or?
Yeah, it is really fast. Especially, I think if we were to, there was an implementation or project that we saw that utilized like an LTE network as like a LTE network card as opposed to Wi-Fi, and that actually proved to be very fruitful because they had like just milliseconds delay. The Wi-Fi was really kind of our hindrance as far as the delay was concerned. But even then, we still, as you saw in the first demo video, we made quite, you know, a bit of stride in the improvement of that. But yeah, it would, I would say implementing or improving upon the networking itself would help with that latency.
Questions? So the YouTube API, is that free?
Yeah.
Is that free? Okay, that's good.
Surprisingly.
Surprisingly.
But it was pretty cool, yeah. It worked out really well.
So then my question is, it's a little bit unclear to me. So that submotor, so what was the issue with the submotor? Is that Windows OS? Is that API?
Yeah. I think it was a mix of like the Windows for the motor and then also Visual Studio too, a little bit, because when I first like downloaded all of the like zip file of the library and everything that you needed, I had to like upgrade a C++ library on my own like Visual Studio before I could even like build the library, and then I had to try it with the like example program. But because I really couldn't configure it with that software, I think that's the reason why it didn't work, because it said it connected initially, so it like recognized that it was plugged in, but it didn't recognize to receive any kind of packets of data. So I think that was because it didn't configure properly of, okay, this is the COM port with the exact configurations that you had.
And we've actually had some experience using some servos before in a previous project we did last semester. And there was a lot of like initial configuration to do with the motor controllers themselves. And then once that was done, you know, it was all set up. You didn't have to redo all that. But I think that was kind of a similar situation we're running into. But of course, yeah, the Windows OS really kind of limited us on that software.
So time delay, so you achieved that 1 over 2 seconds
Yeah.
using YouTube API. Okay, I think the 1 or 2 is okay.
Yeah. We ultimately we would like to try to improve that using like I said, like an LTE, like more of a metered connection.
Mm. Okay, so I think that the Sham's questions, I have the very similar questions.
Sure.
You mentioned that if you have a better camera, let's say high resolution of a camera, then it is much better in terms of immersive experience. But that also caused that the larger
I'll slow
data
it down,
is
yeah.
Yeah.
right? So some trade-off, right?
Yeah, exactly.
So how do you think that? So what's your opinion?
The project that I was speaking of earlier that did end up using the 4G LTE network card, they only had a latency of, I can't remember, it was just milliseconds. Yeah, it was maybe, I can't remember, maybe like 300 or 400 milliseconds. It wasn't very significant. And they were using a 360-degree camera. So I really think that we were kind of hindered on the Wi-Fi aspect, especially because we couldn't, for some reason, the Raspberry Pi was not cooperating with our personal Wi-Fi networks. So every time we had to come onto campus, and as we all know, campus Wi-Fi can be kind of spotty and just not necessarily the best bandwidth. So I think that was kind of a hindrance as far as like demo was concerned as well. I think if I would have been able to use like a 5 gigahertz network, then maybe that would have helped a little bit as far as latency was concerned. But ultimately, the future works would really be implementing that LTE card because that seems to be the best communication that there is for this kind of streaming.
Another way you could do that though is like almost trick the user. So then the camera can only go this fast, so we could just slow down the robot. So it's not going faster than the camera can process it. So then it actually just evens it all out.
Good point.
Okay. So LTE, but we need that using cards, right? That equals some code.
Yeah.
That is another.
That's a whole.
Yeah, that would be a whole
thing.
other, handling all of the programming for that. So that would be future works.
Okay. So then so again, you said that so you had a traverse the issue with that device after you upgraded to the 8.0.
Yes.
But that is only controller.
Yes.
But how about the
headset? I did have some problems initially. For some reason, it actually completely uninstalled all of my Oculus apps and my library and everything. So I had to completely reinstall Oculus on my Android device. So that was kind of a whole different issue. And I believe that the Oculus version that it installed was it was the Oreo compatible version. And I think, there were some bugs in there because the first time I booted it up, I went to click my controller and it just had a stop, like a stop sign on it. And I couldn't figure out why. And I looked up, I did some research on it. And it seems that there's quite a bit of a problem with the controller itself. I don't know. I think it has to do with the Bluetooth. Honestly, that's kind of where it seemed because I even tried unpairing, reconnecting, doing the whole process over and it's still. But as far as the headset was concerned, there was one thing there was some latency between, because there is a touchpad on so there was some latency between that, but it's still, I don't know, the touchpad wasn't the best implementation either, honestly. It was just kind of the controls in general just were very.
Yeah, the touchpad is like the hands-free version of using VR, where you're not actually doing anything complicated that you would need some directional pad. So it's literally you move your head and you have just a pointer in the middle of the screen, and then you just tap to select anything. So it's not really practical for anything that's complicated.
And even then, there was one instance where I was trying to click something, and it was seeing that I was clicking, the button was depressing, but nothing was happening. And I verified, my connection was fine. I had Wi-Fi connection. Everything connection-wise was fine, networking-wise. But it seems that there's just some bugs with, I don't know, the controller input, I guess, because I would imagine, the touchpad uses the same OVR input class that the controller would. So it seems like maybe there lies some issues with that actual, the Oculus API itself.
Yeah, it's actually new. Oculus just made a deal with Unity to even create the library. And then it's also Facebook owns Oculus, and then Google is So it's basically
So it's kind of murky waters there. But like I said, you can't even use the Oculus API unless you use Unity 5 and up.
So I have two more. I think a time is running. Just one more question. So now you are using Galaxy, right? Samsung Gear. Is that Samsung Gear?
Samsung Gear VR.
Gear VR. But Oculus is different brand. But still, you can use that Oculus API.
Yeah, Oculus is a brand owned by Facebook. Like Facebook.
But the Samsung is a completely different brand.
Yeah.
But still,
They partnered with Oculus to create all of the functionality.
Okay.
So because you cannot develop the Gear VR actually runs on the Oculus OS.
Okay.
So they've made that partnership and used the Oculus. So everything you do within the Gear VR requires the Oculus API.
Okay.
Hence the Unity 5 and up.
Yeah, because it's an Android app, but it has Unity wrapped around it. So we did all the programming in C# rather than doing it like in Java.
In Java, yeah.
Okay. Okay. Right. That was. Right. Thank you so much.
Does your API have any support for handling stereo cameras?
We need to restart this.
What?
We need to restart it.
What restart?
It's done.
Because all of the
This is not on.
virtual reality implementation is just single. Yeah.
Go.
So I'm not sure. They do have
What are the
does like
Just
a-
keep it a bit.
you're able to view music videos in Google Cardboard.
Yeah.
No.
Splits it. So yeah. So I think maybe because of that, I think maybe that might be possible. I'm not sure though, honestly.
Okay. Good. Thank you.
Can't clap.
Thank you.
I think that Daniel and Sushi, yours is on Google Drive. Is that correct?
Yes.
Oh, okay.
Haven't to
Just don't move it. The whole thing.
Good. So do you do you have account, the Google account?
It should be that way if you just click the link. Then you will.
Oh, really? Okay, then I can download it.
And it sets anybody can see it.
Okay, that's fine. Just let me see. Give me a second.
left.
Why? I think both of the screen is not. I did that. Oh, it's done. Okay, come on.
There we go.
Let's just.
Yep.
Yep.
Fish. Where's the?
That's good questions.
There you I'm Daniel.
Hi, I'm Piyush, and we will be presenting about our project.
Once again, we're going to go a little bit over what our project was and what we did for our project. So I'm a senior in CIT in software for material systems. I have some Android development experience.
And I'm doing my master's in computer information technology, and yeah, so
So once again, our problem introduction to see if we were able to do what we said we were going to do. There are lots of different things that we thought this could be applied for. So we have sometimes our pets at home. We want to see if it's okay if it needs food. We want to check on a kid while we're cooking dinner. Leave stuff at home,
check the baby's napping without having to open the door and go into the room ourselves. So we wanted to create a way that we'd be able to look inside a room that we're not in.
Yeah, so what we are going to do is we are going to see that whether the video camera that we have connected with our iCreate Roomba, that will be able to stream the video captured to our phone through an API. Also, we will be able to control a camera, or control the movement of iRoomba through our robot. So these are the objectives for this. These were the objectives defined for this project earlier.
So our idea was to have an iRobot that we're able to move around from a phone, and then be able to have a live video to see what the robot's seeing, even when we're remote. And it'd be nice to be able to speak to somebody with an encouragement or something. This was our original mock-up. So my laptop broke over spring break, and so I had to totally recreate the project. And so this isn't what we built it based on anymore. But this is our original concept. This is what we thought we were going to be doing. So we take the Android phone, be able to give it Android messages, voice messages, driving instructions, send that over the internet to a robot, and it's going to be able to react off of that and then send back a video feed from that robot. So the different things that we need the Android phone, an iRobot, a working camera that's compatible with the Raspberry Pi, which I forgot to put on here. And then we also need the Wi-Fi connection that we connect to.
Yeah, so we have created Apache server, and we have used some basic HTTP libraries, socket programming in the language for Python, and then we have created a server that will be able to host a website, or host a connection in which we can pass a post request or get request in order to send or receive commands through mobile and read through this server in our Raspberry Pi. So I've also use socket programming to read whatever the post command he's sending from his mobile API through his speech or through his the movement control. And once I read the command, then I have also in that post or get request in that header file, I extract the relevant function, and then I control the robot. I create Roomba through that. I've also created an API to control create Roomba, and I'm directly calling the functions from the server.
And so his responsibilities were mainly working with the server and getting that side on the Raspberry Pi set up, and then I was going to interact with that from the Android side and work on interacting with the video that resulted from that. And so the initial focus for building that, we wanted to focus on being able to get a way to communicate with the server. We had to get the server working in the first place. At times it felt like we were two puzzle pieces and both of us need the other one working first in order to be able to interact with each other, because we couldn't really tell who needed what. And so eventually we figured out that one of the problems that we were having is that we had to be on the same network. So we decided to use the CIT dev network, because that's the one that's here in this lab. Connect to that, be able to use a local host hosted on the Raspberry Pi, and be able to use a web page, to be able to see if I'm actually able to see that, and then we were able to interact with it. So eventually we were able to send a JSON post method, send some data over just to be able to get to receive that from that. That took a little bit of time to figure out how to interact with the JSON posts. I hadn't really messed with that too much before at any level, so that was a good thing to learn. And so next, we wanted to make sure we get a video. And so we weren't really sure how to do this. There are pretty limited ways that we could use to be able to get a live stream video. They used a web page. We thought, man, do we really want to record segments and then send that over? That's probably not the best way to do it. Then we realized that we didn't have to reinvent the wheel. So we ended up using YouTube Live. So we created a way to be able to see a video that's live on YouTube and we'll send that over and restrict the privacy settings to where only people who have the link can see it. So that way it's not like a public thing to where anybody can watch it at any time. So we use this pre-established API to be able to watch the live stream without having to reinvent the wheel. And so on the app itself, we decided to create a YouTube fragment that was going to be at the top of it. We went into Google, got an API key to be able to interact with that. And then, so at the top of the screen, you'll be able to see that there's a YouTube feed. And then on the bottom part are different ways to be able to control it. So we made sure that we were able to watch videos, and then we made sure that we were able to watch live videos, and then we were able to connect our own account from YouTube Live. It had a 24-hour wait period, so that was a little bit nerve-wracking if we were going to be able to get set up in time, but we were able to. But there is an annoying bug that happens with this, and it requires the setup to be done in the onCreate of the activity because of the way the layout happens. Because if anything else happens to be on top of it, then it's just going to mess with the YouTube fragment and corrupt it. This is an actual bug that's on the YouTube Stack Overflow. They have it listed as a bug that they're needing to fix. And so I wasn't totally sure what could happen to be doing this with this. So I realized that if by rotating it or by going full screen, it could happen. But if not, it would only load 1 second at a time, which isn't what you're wanting it to do for a live video, especially. So for ease of use, we decided that what we had hoped to do is do an edit text button and say, okay, here's the link that we're going to, and just go to that link and then populate the YouTube fragment from that. But we ended up having to hard code it in, so that's a little bit of a bummer. We did try the edit text thing, it just wasn't working with this bug. So for ease of use, it's not necessarily the easiest, but it does work. So the grand review of the UI. So at the top, we have our lovely, in case you didn't know, we're YouTube sensations now. So we're there at the top, getting ready to record a live video, and we realized at about 11 o'clock last night that we had said that we were going to implement speech functionality. And so we got that working pretty fast. So we wanted to be able to control the robot from the phone. And so we have different directions that it can move in. And then we have a stop button. And then we also have a speech button that can do all those same 5 buttons that you see below it using the same word. And I think you can also say go and it'll do the same thing if I remember correctly. So we also have the YouTube video that's up there on the top. And so for the speech to text, we're going to give it an instruction. We're going to say left, right, stop, back. If you say go by itself, then without saying any of the other words, then it will just go forward. If you say go left, then it'll go left first because left comes higher in the priority. And so it's going to call the same commands to be able to steer iRobot around the room. So one of our other problems that we ran into is that we ran out of USB ports available because of the way we set this up. Because we weren't using remote software, we were directly connecting a keyboard and mouse to it. So we ran out of that. And we also, so I have my own USB camera that we used and we attached to it, but it turns out it's not Raspberry Pi compatible without figuring out what libraries went to it, and we couldn't figure that out in the time that we had. So without a Raspberry Pi camera, we were limited in our ways to be able to record, but we were able to eventually get around it. So how can we record a live video without having a camera? We discovered that by having a YouTube video being recorded live from the laptop, we can put the laptop on top of the Roomba.
Yes, that works.
And it guides it around the room the same way. So let's see here. I think this is forward facing. Okay. Okay. So
Yeah, it will be a bit tilted.
So what we can do, so we have this live video that there we are setting it up. There's a little bit of a delay. I think it's 8-second delay.
Yeah, you cannot.
It's a
only 8 seconds.
It's a 2-second delay on the laptop, so I don't know why it's so slow. But so we're going to move forward, and so
I don't know. Maybe
do we can disconnect?
You picked it up.
Oh no! Oh, I picked up
okay.
the robot. Okay. Okay. So I'm going to hit the forward button.
Is it?
It should go forward. Oh, did it die again?
I don't know. Is it dead?
No, let's see.
Okay.
Oh.
See, this is what you say about live demos.
Yeah, that's why I told you. We
We did record a video in case this didn't work. Okay. So it says forward. It's not picking up. It was picking up a second ago.
Just forward. Let me.
I had it doing when we were walking up.
Yeah, I know. I know.
Okay.
Okay, nice.
Forward.
Something happened.
Maybe closer to the mic.
No, it's not.
It shouldn't be. So it's connected to the CIT dev network right now.
Are you connected to the CIT dev?
I thought it was. Yeah. Because when we were walking up here, I hit the button and it moved.
Wait. Anyways, till that time we can play the video.
Oh, this is a great video. But we also have speech to text working, and it should be picking up because it was on the console.
The robot died, so it mattered from out of passive and safe mode. That happened to us with Python program.
Is your robot charged? Can we use the way?
Mostly, yeah. You can go.
Right, we're going to try.
Wait, just.
Wait.
We can just play our demo.
Okay.
It's okay, I will try. What happened to this?
We saw it.
Yeah. You saw it working? You
Yeah,
see it?
yeah, I saw. And I saw that, yeah.
Okay.
Something changed.
Okay. So because we had because we have to get the live video with the link connected to it, there's a small delay of when the start time of the live video is compared to when it can actually be shown. So we have about a minute of us sitting there recording. So we probably don't need the audio for this. But so right now,
You need the audio?
maybe let's make it quiet in case I need to talk over it, because I'm pretty sure that's going to have to happen.
No, it's mute. Can you restart your
Start the app.
Yeah.
We're going to let the app start whenever it feels like it's a good time to start. Because that's just how Android is sometimes. If I were a teacher, this is probably the awkward process I would always be in between every class. And then I have to try to cover why everything isn't working. Good thing Dr. Mid never has that. The laptop.
Oh my god.
We are not sure how secure this is going to be. So if the laptop breaks, I better get an A, Dr. Mid.
That's very tired at this point.
What time was that?
11,
11:30.
Never mind. You are not facing front. The laptop camera is not facing the front. Yeah, now here we go. You ready to move backwards, class? Here we go. Whoa. Stop. Then now we're going to move right. Now left. Now forward. Now
Oh,
back.
that's good.
Now we're going to stop. And it's basically, we
Okay, I think that the view is from laptop, not on the phone.
Yeah,
That's why this is real time. The view is the screen.
But this is uploaded on
this video.
this is being recorded from laptop.
Okay, that's why there's
Yeah.
no delay.
Yeah.
So it
Or
is
no, there's a separate tab that was watching the YouTube video with only a 2-second delay
Yeah.
So I can turn on
from the web. So it's something to do with the Android YouTube API. That's what's slow and causing the 8-second delay.
left.
Which I was surprised that they allow because like there's some YouTube video game players who, if you can see what another player is doing from their screen live, then that's a real advantage. So I thought that they'd have to plug in delay, but it's not as much as I thought they would.
Anything else that you think we should show for demonstration future? I think that'll be a
So that's But we did have.
short video.
I was controlling it using speech. So that's.
Oh wait, that's not the right stuff.
It's a very good demonstration video.
Let's try it out again.
All right. Forward.
Oh, very good. There we go.
Stop.
I think so.
And now stop. Okay.
What
And
happened?
so now
I don't know. That means
we both of us restarted. So
Okay.
I hit left. Now it goes left. Now right. Stop. So now I can back up. Or it should be interesting one. So now I can do that. Okay, and then we can also turn on the live video and see our recording. So if we put the laptop on top of this, then it does it all at once. There's just
Yeah, but it is
significant delay.
Yeah, 7 seconds delay. It is happening.
So I can say
Oh, it's good.
left, and now it's going to start turning left until I hit stop.
It is like forward, I think so. So this is like a basic demo version that speech or with API, mobile API, we are through server we can control iRoomba. And the only thing is if we are able to, factor the latency or somehow control the latency and make it real time, then we will be able to control through means without being in the room we can be able to do that. But right now since there is latency, so we need to be in room in order to move these things. So.
And so one of the things that we considered in order to deal with that for future works is that in order to help with that latency, we'd want to create a way to where if I hit right, then it go right for about 1 second and then stop. And then that way, if the camera has to readjust, then you have time for it to readjust and see what happens. And we also didn't want to program anything with sensors because if it hits something and then automatically starts turning around and you can't see what it's hitting, then that's going to be really frustrating. So we didn't want to program that in. So most of this, we did look into if we could do this without it being programmed, hooked up to a wall. And it turns out that we would be able to. We could get a battery pack to plug into the Raspberry Pi. And because this is based off the Wi-Fi network, then we can attach it all to the same place. We just didn't have the right parts for the camera and for the battery pack to be able to do that. But this is something that could be moved around. It would depend on a Wi-Fi network, which is kind of a bummer.
So
And
right
also
now
fast
we have
access.
connected to means I checked with like 2-3 the server thing. So anything that is connected to the local thing, and if you are connected to that network, so that will work. But if you both are not connected to the same server, then that is not gonna work.
Is that firewall or why?
What?
Firewall or why?
No, firewall. So because I'm setting the Apache server on this, so it is on a same network, and means either I will have to like port forwarding or means like do more programming in order to redirect.
We could
from other
register our
server.
domain, and that would solve that problem.
So either you have to be in same domain or you have to make an URL address and give it to.
This can be used as security to like go through the hallways and be able to look at things with your phone and be able to like see if anybody's going down that way while I'm walking this way. So there's some security applications that we hadn't quite realized at the very beginning, but just because of how mobile it can be, that it's a pretty good advantage to have. So any questions?
How would you improve the latency? I know you said like that it was quite a bit to do with the YouTube API itself, but I was thinking, since you do have the like LTE functionality of the Android phone, do you think you could implement something like we were talking about too? Or what are your thoughts?
So we could, I don't know. It's hard to, as far as what we saw, there wasn't a good statistical way to see where the biggest latency was.
Yeah.
A lot of it's speculation.
Yep.
So part of it could be the laptop connecting to the network. I haven't used CIT dev besides this, so the CIT dev network itself could be slow. And if we're hitting that 2 ways, then that's twice the latency.
Yeah. Also, I think so between me, since we are uploading it to YouTube Live and then it is linking it back to our mobile, so there has to be some delay because there is some kind of communication between 2-3 bits.
Right.
There's not very much delay between the app and the Roomba though.
Yeah,
which
because it is
good.
local thing. But once you go to server of YouTube, because if you are uploading in YouTube Live, then we are uploading in YouTube server or something like that. So we have to communicate with that. So I think so there is at least 2-3 seconds kind of delay between communication between YouTube and this thing. But our camera thing, I don't know. Means even while serializing and means I was looking at codes how to means how to make sure that you have live feed in your Android or anything. So in that, most of the things I found out that there has to be some kind of latency. You need to figure it out. But yeah. So then also the codes were very big or libraries means. So it's like you just hit and try. I was trying it out, but it didn't work in the timeline.
But then again YouTube API, but then there's always latency. Is that your?
No, this is not. But I'm saying if everything is fine, if you are going to post this on YouTube or something, and then read it from YouTube, then there has to be latency. But if we are trying to do it locally or if we find somehow.
So what do you mean by locally?
Locally as in, yeah, so we can use, like make a separate communication channel that will, through serialization and deserialization, it will directly pass the video through mobile. We can also compress the video, like
not through YouTube.
No, not through YouTube. That's what means. The other route will be big. The YouTube route was the simplest way to make it working.
Okay, then my question is then, what's that for? What is the YouTube for? The API for? There's always, it sounds like there's always delays.
Continuously streaming a video and then figuring out how to encode that into a fragment based on whatever the video type I'm getting was really complicated when there's already a solution available.
Then it's not really live, right? I don't know.
Like if we were to watch a YouTube video on there, then it's about a 2 or 3 second delay. But when I watch it on the phone, it's a little bit slower, and I just don't know what
So
that
my
is.
question is not about 8 seconds. My question is about 2 or 3 seconds. Right? It's not real time anyway.
Yeah.
So that's why I'm asking. That's my question. How to overcome that 2 to 3 minutes, 2 to 3 seconds.
I'm not sure.
I had a question about the text to speech. Is it basically once it recognizes like the keyword that you're looking for, it immediately executes the command? Could you just, because like you said
I
move
can
left and it would
demonstrate.
just automatically start going kind of?
Yeah. So what it does is I hit the speech button, and it has a little mic that pops up,
Yeah.
and then it's going to process and look forward. So if I say left and stop speaking, then it's going to search that entire phrase, and it should do that. But because I gave it such a long phrase to search, it's probably not going to. So it looks a lot better if I just say forward, and then it should start moving forward. So
Okay, but like once it finds it, then it like starts going, or you have to hit start stop on both things?
it should just go automatically. So if you say
Okay.
left, and it's
So
going
I
to
think
start
that there
turning
is
left.
also latency between once you press something, there is 1 second or that kind of video. But these things, I was looking into net, but I was not able to somehow it is quite less, but it is by speech also I can find out there is latency. But I think so since you know while we have also the pattern detection also in communications between servers, so I think so it will the server is also listening always and processing it, so it will take some time, like some milliseconds, but I don't know.
Questions? No, okay.
I think it was clear.
Really good. Okay, any other question?
I like the perfect.
So just in your mind, what would be your future work?
The future works. As we said earlier, being able to get it remote with like the battery pack and being able to have it all self-contained would be really nice. Being able to see what the latency between like the Raspberry Pi camera to YouTube would be, because just uploading to YouTube by itself seemed to be causing some delays that we weren't really sure. So maybe creating a way on the server to record a live video and stream that directly.
Then the last question is, what would be your contributions to Team?
As I said earlier, he worked on the server side for the most part, and I worked on the Android side, and then we worked together to combine them.
Okay, that's good. Right, this is also very interesting project, and thank you for showing us live demo. Okay, good, thank you. Yeah.
For the science first 5 minutes, I thought.
They're always, that happens all the time. Okay, all right, guys. So now we conclude the class CNIT 581 SDR. So I'm hoping that. I'm sorry. Feedback.
Okay.
Oh yeah.
Okay.
I'm pulling you.
Thank you. Here. Right then, thank you guys. I hope that you learned this class help you to get some idea about robotics, and then it broadens your knowledge and also open your ideas. And then I hope that I tried to put some interesting topics, and then I tried to cover very diverse topics throughout the semesters. But sometimes we couldn't, due to the limited time and the scope, we couldn't really dive into very detailed topics. So I chose that rather, the dive into one topic, I just rather, cover the various topics. So I hope that, that helped, and then you got some idea. And then, my doors is always open, and then that I'm very robotics person. So if you have any good ideas, or if you have any questions, anytime just drop by or shoot that email. So, we can, keep in touch, and then, I'll be always, there for you. Okay, so thank you for being good students, and then thank you for doing very good and then very inspiring and very innovative the project. So I'm hoping that I learned a lot from your project, and also I'm hoping that you learn from the project as well. So we are very small groups, so I really like that cultures, and then I really like that interaction. We can the question, giving the question, answer each other's, and then helping each other. I saw that not only the project, the lab, I saw that you guys help each other and then help each other. That was I really like to see. So, thank you again, and I hope that you have a great summer. And if you are graduating, the congratulations. Are you?
Yes.
Are you? Oh my gosh. So let's keep in touch. I'm hoping I'll be here for the next 10 years. So, let's keep in touch. All right. Thank you, guys.
Thank you so much.
Okay, then,